Our next speaker co-founded the biotechnology company developing technologies for microalgae valorization, Algae. She will share her expertise on the topic of CO2 in the microalgae value chain. Please welcome co-founder of Algae, guest researcher at the University of Tartu, Dr. Liina Joller Vahter.
Thank you. And for a start, I join with others for congratulating organizers, particularly Kaspar and Ilona, on this wonderful event. Yes, so I'm Liina Joller Vahter. I'm coming from Tartu. I have a dual role. I'm economist by background and microalgae enthusiast, we could say, as well. So actually I plan to go a little bit even beyond the CO2 aspect, and I was inspired by the title of the event, so looking a bit more like in the circular aspect. But Michael already started with a background of microalgae. I didn't know exactly what he's planning to tell, so I will explain quickly what microalgae is, how they are usually cultivated commercially, where can they be useful, and how they relate to circular bioeconomy, and including CO2. Then briefly about some experiments and projects that we are running together with our partners at Estonian University of Life Sciences, as well as consortiums of international partners. And I will touch briefly on regulations and the markets as well. So microalgae. Many of you, of course, are well aware of the different microorganisms, but those who are not, just try to imagine something which is so small that you can barely see it, and it's like you could imagine it's roughly half of the diameter of your hair. And yes, they grow in water environment. Most commercially used strains are photoautotrophic. Some of them are heterotrophic or mixotrophic. We have used so far only photoautotrophic strains. And commercially used overall, the estimations range from 500,000 to 1 million different strains around the globe, potentially. And only a small fraction of them is scientifically studied to some extent. They grow in saline or freshwater, in different environments, starting from really hot springs to icy landscape, different acidity levels, light conditions, and so on. Some of them like to live in colonies, and some are more, let's say, egoistic. Yes, and they are rich in proteins, carbohydrates, and lipids. There, of course, there's the numbers don't sum up here, but some strains are known for some properties, and let's say chlorella is well known for rather high protein content, and at the same time the growth conditions also play a role. And some of them can be even toxic. At the same time, some of them are of potentially very high value and even usable in the farmer sector. So how they are grown? The first picture is from the lab in Tartu. So basically, in the small bottles, the process usually starts. Then it's upscaled to inoculum, and further used in larger growth environments. Below the picture, let's see. Okay. The picture here below is from Netherlands, and this is one of the examples of so-called raceway ponds. And the cultivation methodology really depends that how you want to use the biomass afterwards. Open ponds are usually provide you cheaper material, yet lower quality. The question is, of course, always about the suitability of climate. There are places in Southern Europe as well as Asia where open ponds are very common. At the same time, in the Nordics, we can talk more about closed systems. And also we are using and developing photobioreactors, meaning that the artificial lighting is important part of the technology and important parameter. And processes vary from batch approach to completely continuous. This is just a glimpse of, as far as I know, the largest photobioreactor system in Europe, located in northern Portugal, close to Porto. So you can see basically the walls, two walls are approximately 2.5 meters high. And this particular site is located outside, so the tubes are outside, whereas in most Central European locations, as well as, for example, in Iceland, the tubular systems are located inside the greenhouses. So this is just a flashback. We started already in 2013 with a kind of crazy ideas about valorizing microalgae, and this was this was our first pilot prototype. So blue and red lights, as usually in photosynthesis, then they are most useful for enhancing the photosynthesis. So what are the common applications? There were times some 25 to 20 years ago when there was really big hype about algae-based fuels in USA, as well in some inspired from USA, also in some other countries, but that resulted in a big disappointment. So nowadays, and especially when we think of Estonian climate, we aim for the applications in the higher levels of bioproducts pyramid. If you can imagine that this it's a pyramid here. So in pharma we don't do anything yet. We have projects going on in the feed and some plans for the cosmetics industry. Hopefully we can start with them quite soon. And for food, basically it's technology ready to be upscaled for commercial. So its technology is already existing. And although the pyramid is often used as kind of approach to strive higher and higher in these levels, then what we have also learned is that definitely we need to look for the best symbiosis and what we to use first the most valuable compounds, and then in cosmetics and pharma, and then for rest we could use for biomaterials, for example. Okay, coming back to the CO2 aspect now. So basically what the microalgae needs, if they grow inside the photobioreactor, they need CO2, they need light, suitable temperature, growth media, nutrients, and the culture itself. And the growth or the cultivation is basically a natural photosynthesis process. And when we are able to ensure that the gas that goes into the photobioreactor, it's estimated that up to 95% of the carbon dioxide can be captured. So not all of it, and even maybe that is on the upper limit. So still some part of it goes out, and also like on average, the 1 ton of carbon dioxide is captured by growing 1 ton of microalgae biomass. Okay. Some challenges with these numbers. For example, that the CO2 capture numbers are usually published in per unit of dry weight, and it can be that the dry weight, the humidity percentage is not disclosed. It can be basically something between 2 to 10 easily, and this is already quite big fluctuation. Quite often microalgae CO2 capture capacity as well as biomass production capacity is compared with other crops per land unit, for example, per hectare. Again, what I have heard per hectare estimations is that it ranges from something like 50 to 200 tons per hectare, and that's from European pilot sites. We have not measured it ourselves because we are still in too much in the pilot scale, so the estimation calculations would be not so reliable. Or, for example, per liter of reactor capacity. As you saw, the reactors can be really in a variety of shapes and sizes. So it can be vary also heavily how many liters per hectare your reactors hold, and of course per investment units. Yes, and the challenge with this microalgae capture capacity is that the studies that I have seen so far are basically all still made on the lab scale or very small pilot scale. So if someone is doing it on the large scale, it's not disclosed. Now I go to one of the, actually 2 projects, which one is about to finish in summer, and another one just started. And they are both related to some extent with using flue gas or carbon dioxide from flue gas as the carbon source in the same photobioreactor. Yes, so basically the question, one of the questions that we tackle in these projects is that if we know that flue gas has, besides the carbon dioxide that we want to use, besides that, it has also heavy metals, but potentially some other toxic compounds that could inhibit the growth or just limit the biomass use at the end. So how much of it really goes into the biomass, how much of it goes through the bioreactor and is released with excess CO2 and together with oxygen, or does it, or do they go, do they exit the process with draining? And therefore, we have currently ongoing two tests, or 2 phases are in the focus. One is the toxicity tests of dry biomass, and another is fish feed trials. So today I can share the first results of the biomass tests, and we have. I don't think that this works. So basically, we have on the left table we have CVC referring to Chlorella vulgaris, commercially available in our shops, in some supermarkets, or in specialty like health for nature's natural products shops. And the CVF refers to Chlorella vulgaris grown on flue gas in our lab. And what we see that like we have tested for actually more potential toxins, but the main things that also the food authority is keeping track on show that if we use flue gas, it does not go. The resulting biomass is not affected more than what is already available on the market, nor does it exceed the limits that are allowed by regulation. And on the right, on the table on the right, we have comparison of again on flue gas grown chlorella and chlorella grown on ambient air or atmospheric air. So basically, I must say I cannot explain all the changes here, and I have some doubts that at least for the pigments or chlorophylls and carotenoids, we need to repeat this test. But we see that it does affect to some extent the composition, but yeah, okay. I will jump to how much time I have. had a thought with this slide, and I forgot it now. Okay. Yes, and additionally, I wanted actually to give credits to Reinu and Koit, who have been doing a lot of work in the lab for this test, and advice from Timo. Yes, and now the lab part is nice. But as I started with that, actually I have a background in economics, and my role in our team would be to actually find the best commercial applications for this. So what I really run against the big wall is when it comes to regulations. If someone wants to go into details, it's references to look further. Even if the regulations, even if we use the materials that are existing in our nature, we are not using GMO or engineered cells. And if we aim at some point to start providing ingredients to pharma sector, it gets even more difficult. So what I can summarize here is that especially when considering the circularity perspective, using specific strains, using specific methods, using specific nutrients from side streams, agriculture or food side streams. There are so many potential obstacles in getting the final product to market, even if you are able to do it very well and kind of seems that it's profitable in the lab or pilot scale. About the market and monetization, a few words as well. So I thought I will just take one estimation of the market from the European Algae Biomass Association, estimating that in, let's say, 6 years, the market could reach 9 billion euros. And especially in food, cosmetics, pharmaceuticals, and energy. So I started with being hesitant with energy already. So perhaps not. Let's not touch that part. And today, the different microalgae biomass and its derivatives, like it depends on the strain, on the purity, on the quality or purity, very much. But starting from 10 euros per kilogram to up to 1,000 euros or even more. And sometimes we were also there 10 years ago, and even now sometimes I hear that people are planning to use, as microalgae are capable of capturing CO2, then people are planning to build a business out of capturing CO2. And a rough estimation with today's market price of carbon credit, which is around 60 euros per ton, and assuming the conversion rate, so per 1 ton of biomass, we could get a bit over 100 euros of carbon credits. And even if we would sell the biomass at the lowest price in this price range, saying 10 euros per kilo, meaning around 10,000 per ton. So it's quite obvious that yes, it's potentially a revenue source, but not but just a small fraction of the whole potential. Okay. Something that I still wanted to emphasize. Yes, I'm very much fan of microalgae. However, I am seeing the potential in the future world for microalgae in symbiosis with other novel protein sources, including fungi, different organisms that have been mentioned here today. And yes, and when maybe some comments as we are gathering here, mostly the people, mostly Estonian people or people working in Estonia on this topic. Yeah, it may seem at the first sight that the Estonian climate is not so friendly for this kind of activities. Yet they are, well, we know that in southern countries they need spend energy and water for cooling, for example, and also maybe we cannot grow it all year round because of lack of enough sunlight and too expensive artificial light. But we don't grow potatoes or wheat all year round as well. So, and besides, there's always potential to export Estonian know-how. I will finish here. Over time already.
Thank you. So, questions?
Yeah.
I have again the energy expenditure question. So what is the amount of energy required to fix with your technology 1 kilo or 1 ton of CO2?
Yeah, the question, I don't have concrete number because there is no single technology. At the moment, we are still experimenting with different approaches. Yeah, I don't have a concrete number, sorry, at the moment. If you're here tomorrow still, I can come up.
Okay, one more question.
Thank you for your talk. My name is Mari Eskola. I'm from Medfiles, Finland. And I just got in the door when I started to hear a nice talk about microalgae. I'm from the company who is providing regulatory assistance to your type of companies, to which regulatory line to take. And it got to my ear that you were thinking whether it would go pharma or food or feed or perhaps cosmetics. What I see for my clients or clients in my company, often your type of people or the companies go first to feed or cosmetics because that's far easier route than the food route. The food route often gets classes in the novel food regulation, and that's a quite tedious way ahead. So that's just a little advice from my side, and if you're interested in further discussions, here I am, and tomorrow as well. Thank you.
Thank you. And actually, you are part of our consortium, as far as I know.
Okay. No more questions, and thank you for a nice talk, Liina. And now we are breaking for lunch. So lunch will be till 14:15. So please be back by 14:15 here for the next session, Foods, Materials and Beyond.